Hey folks, I would like to give you a quick introduction to normal distributions to supplement our old friend Participetti. So let's see what I got for you here. First of all, the normal curve is just a representation or a model of some underlying data which we could represent using a histogram. So if you look here and you see the histogram, you'll see that the normal curve kind of traces the edge of a histogram that is symmetrical and unimodal. So what do the bars in a histogram represent? It probably would be a good time for a reminder, because if you don't understand what the bars in a histogram represent, then it'll be tricky for you to figure out what the normal curve represents. So each bar in a histogram represents the count of values in a specific interval. So for example, if we came down here and we looked at these values of x, by the way, in a histogram, a histogram only represents a single variable. And that single variable we'll just call x for right now. And down here on the x-axis are all the possible values of x. Any particular bar tells you how many values of x there are in a particular interval. In this case, I'm pointing to an interval between 100 and 110. And we can see that the bar for that is at about the 30 point, which means in this particular data set, there must be about 30 data points that are in the range from 100 to 110. So when we look at a normal curve, if we have an x-axis that has values, the normal curve tells us that there will be a lot more values in the center of the curve at whatever value that is, and there will be fewer values at either edge of the curve, the right edge or the left edge. As I said earlier, the variable of interest, we could call it x, we could call the variable of interest y, we could call the variable of interest a number of things. In a minute, we're going to be looking at roller coasters, and we'll call the variable of interest top speed. But we can still call it x too if we wanted to. Okay, so here we go. Let's take a look at some roller coaster data. So I'm going to go ahead and bring this up. And what we can see here is here's some data off to the left, and here's a graphing thing over here on the right. And what we're going to do is we're going to try to look at the top speed of, there's 157 cases. The cases are the who of the data, and each one of these rows represents one case. And in each row, we have a particular roller coaster at a particular park. And what we're going to look at is the top speed for all these roller coasters. And I'm kind of hopeful that you guys could predict what would happen when we go to look at this top speed. By the way, all of the stuff that when we're talking about normal curves, we are talking about populations that we believe could be well represented by a normal curve. And in the case of top speeds of roller coasters, we kind of expect that maybe a normal curve might be reasonable, because we kind of expect most of the top speeds to be about the same, with very few being super fast and very few being super slow, or the other way around. Okay, so anyways, so let's go ahead and take a look and see what happens. So here we go. We can quickly do a little dot plot just to get a sense of, again, as we go up, that is the total number of roller coasters that have this speed down at the bottom. The x variable, in this case, the single variable that we're representing, is all of the different values are down here. And the dots represent specific values along this x-axis. So there is one roller coaster that looks like it has a top speed of 120, and is that kilometer? That's miles per hour. Woo. And then there's a few roller coasters where their top speed is very slow. These three are between 20 and 40 miles per hour, closer to 20 miles per hour. So the dots themselves represent the speed of the roller coaster, and if we have a bunch of dots going vertical, that means there's a bunch of roller coasters that have that particular speed. Okay, now what I'd like to show you is how these dots relate to a histogram, and then ultimately we'll assume that a normal curve represents a sort of a quick sketch of a histogram. So first of all, let's do a little bit of magic here. we're going to go ahead and group these dots into bins like we would normally do in a histogram. And then we're actually going to go ahead and turn those dots into bars. And then we'll see something that we have seen before is a histogram with bars. And I want to go back to our slides here. Maybe I need to go back a smidgen here. So we'll go back just for a second, just to remind you that the bars in the histogram represent underlying data, just like the dots in that dot plot. And the normal curve itself represents data, but with a sketch instead of with bars. Okay, anyways, let me go ahead and keep going, and let's see if I can try to make more sense of this. Now, something that's interesting about a normal curve is that it is a density curve. And I already had you folks take a look at, briefly take a look at density curves using Khan Academy. Hopefully you watched a couple of videos and then did all the exercises. Density curves have certain properties, and there's at least one that's really important, and that property is that the area under a density curve is exactly 1. Now, why does that concern us with normal curves? Well, another way of saying 1 is 100%. Now, for those of you that get a little freaked out by that, let me try to use some information that maybe you can believe. I hope you believe that 0.5 is the same as saying 50% and 0.75 is the same as saying 75%. And if you're willing to believe that, then we're going to call 1 100%. And later when we talk about probability, we'll be bringing this stuff up again. Okay, so anyways, so when we have a density curve, when we say the area under the curve is 1 or 100%, another way to look at it is that the area under the curve actually represents 100% of our data. There it is. The area of the region under the curve. So if we're interested in a particular region under the curve, then the area of the region under the curve represents a certain percent of the overall area. So for example, when we're looking at this diagram here, if we were told this is a density curve, then by definition the area must be 1 or 100%. And if we wanted to know what percent of data is above 4, our x value would be, could be one of these values down here. If we wanted to know what all the x values were above 4, I could tell you what percent of the data this was. And one quick way I would do it with these blocks is I would say, well, there's 1, 2, 3, 4, 5, 6, 7, 8 blocks there, 9 blocks there, and then these two are half a block, so I'd say 10 blocks all total. And if I'm looking at the blocks that are just a greater, where x is greater than 4, there's 4 of them, I would say that 40% of my data in this density curve has an x value that's greater than 4. So let me go ahead and get this out of the way. Just like a sample of data represents a percent of, so the area of a region under a density curve is just like how a sample of data represents a percent of a population. Okay, so that's the analogy we're going to use when we look at normal curves and we're thinking about what does it represent. The whole normal curve represents an entire population, and the part we're interested in represents some percent of the population. Okay, so we are going to use area as an analogy for percent. If you want to know what percent of the data lies below a certain value of x, you just compare the area of the bars. We won't always have bars with a normal curve, but if you imagine that there was bars, for instance, if we wanted to know what percent of all of these bars were less than 50, here the x values are down here, if we said less than 50, we would look at all the bars that are less than 50, and we would add up all of their areas, and we would compare that to the total area of all the other bars. Oh, and something to keep in mind is that the bigger the bar, the higher percent of data. So that means that in a normal curve, we expect most of the data to be in the middle. That means, and that's why it's so important that we only use normal curves when we believe the underlying data is actually normally distributed. And we'll talk about that more as we go through this chapter. Okay, now I'm trying to tell you all this because we're learning something called the empirical rule. And the empirical rule doesn't make a whole lot of sense if you don't understand the concept of the density curve and the fact that area relates to percent. So one thing that's interesting about a normal curve is that the standard deviations are all exactly the same length. If my mean is right in the middle and I go one standard deviation to the right, and I go one more standard deviation to the right, I better darn well have traveled the same distance for both. The thing that's a little weird though is that the percent of data that's under the curve from 0 to 1 standard deviation is a lot more than the percent of data that's under the curve from 1 to 2 standard deviations. So that's something that we're going to try to nail down. It's sort of abstract, and we're going to see if we can really get to understand that idea. Okay, so again, we already talked about x as it could relate to like the top speed of a roller coaster. And here's yet another example of what x could be. X could be whatever. X is a variable. And just like in many word problems that you've solved in your career as a math student, we use variables to represent all kinds of things. In this case, these values of x down here represent the average height of women in the U.S. And as you might imagine, most women are around a middle height, and very few women are very short, and very few women are very tall. And that's what the normal distribution represents to us. But one thing that we use the normal curve for is to help us better understand what percent of a population is above or below a certain value of x. In this case, x is the average height of women in the U.S., so the normal curve could help us to better understand what percent of women in the U.S. are below a certain height or above a certain height, or even between two heights of interest. Okay, so one way to figure out what percent of the population is below a certain value of x is to use the empirical rule and add up all the individual percents like we saw in the last diagram. But there is a problem with this method. By the way, we would say that the percent of a population below 1 standard deviation below the mean would be about 16%, because if we added up all of those little guys, about 16%. In the future, we'll find a more accurate way to get exactly, but this is close enough. The thing is that this is a rather awkward way to figure out what percent is below -1 standard deviations. So the traditional way we're going to do this is we are going to start with numbers that are easier to remember, like the 68, the 95, and the 99.7%, as in the 68, 95, 99.7 rule. 68% of our data is 1 standard deviation away from the mean. That means 1 standard deviation below and 1 standard deviation above. And if we take that 68%, divide it in 2, we get 34 and 34. Now, if we really wanted to find out what percent of data is below 1 standard deviation, below the mean, instead of figuring out all these individual percents with all their decimals, we would simply say this. We would add up the two 34s to say that's 68. We would then say the entire curve is 100%, so if I subtracted this 68, everything that's left over must be 32. That means if I added this bottom part plus this top part, it must all add up to 32, because the whole thing's 100%. And if I divide that 32 into two parts, then the bottom part must be 16% and the upper part must be 16%. So this is the way we traditionally come at figuring out what percent of data is below a certain number of standard deviations from the mean. Oh my God, we did it, people. Woo! That was a bit of a marathon. Thank you for your attention. I hope this is helpful to you. Let's proceed. Let's go do some math.